In this third video of wave properties, we are going to look at how the terms are being used in the description of a wave in graphical format. Okay, so there are two different types of waves form that we can show graphically. One is through a displacement distance graph. Okay, so in a displacement distance graph, it's like I just take a photo of the wave at a particular instant. So it's at one time, okay, at a particular instant. So it shows all the particles, the displacement of all the particles at a particular instant at a time, okay? And because the x-axis is distance, it gives you the wavelength of the wave. So what do I mean by that? Okay, so I have already explained to you what is meant by one wave. So if I were to start from P, okay, one wave will be when I go down and up. So one wave will be when I end at S. Okay, and then the next wave will be from S, I go down, I repeat myself, I start to repeat again, S, go down and up again. So the next wavelength will be at V. So P to S is one wave, S to V is another wave. So if I were to start from Q, okay, then one wave will be I go down and go up to T. Q to T will be one wave. That is when I start to repeat myself again. From T, I go down and up again, okay, up to here. Okay, that will be my next wave. And if I were to start from R, one wave will be I go up and down. U, R to U will be one wave. And then I'm going to repeat myself again, up and down, okay, to get my second wave. So these are one wavelength. This is also one wavelength, Q to T, R to U is also one wavelength. Okay, because the x-axis represents the distance, the length of one wave. Okay, next, I can also represent in graphical form in terms of a displacement time graph. So a displacement time graph for the x-axis will be the time. Okay, it shows only one particle that is moving over an interval of time. So it's not at one timing. Okay, I just zoom into one particle and how is this particle moving? So this particle is moving up and down over a period of time. Okay, so from a displacement time graph, since the x-axis is time, I couldn't get the wavelength. I couldn't get the length of one wave, but I could find the time for one wave. So the time for one wave is known as the period of a wave. Okay, and when I can find the period, I can find the frequency. Okay, so I zoom into what exactly is period and what exactly is frequency, as well as recap on what is wavelength. Okay, so the period, okay, period T is the time taken for each point on the wave to complete one oscillation. Okay, in layman terms, it means the time taken for one wave. Okay, period is the time. Okay, how to remember period is the time? You can remember it as one period of your lesson is 20 minutes. So it's a time. Okay, so period is a time for one complete oscillation. SI units will be in seconds, but depends on the x-axis. So sometimes the x-axis can be in hours or minutes. So the period of a wave need not always be in seconds. It can be in hours or it can be in minutes. Next, frequency. Frequency you cannot get directly from the graph, but you can get you can calculate it from the period. The period can be gotten from a displacement time graph. Okay, then from there I can find the frequency. Frequency is defined as the number of oscillation each point completes per second. In layman terms, it just means the number of wave generated in 1 second. Okay, and then sometimes the question can be in terms of wording. So they will tell you, oh, how many crests or how many trough has passed through that point per seconds. Okay, and the SI units is hertz, capital H, small letter Z, hertz. So how do I get the frequency? There is a formula. Frequency is 1 over period. Period is big T. Frequency is small f. Okay, so it's in layman terms, it just means how many waves are there in 1 second. Period is the time time for one wave. Okay, one complete wave. Frequency is how many waves in 1 second. So if I have a frequency of 5 hertz, means I generate 5 complete waves in 1 second. 10 hertz means 10 complete waves in 1 second. Okay, so the higher the frequency means the faster the vibration rate. More waves are generated in 1 second. Okay, then wavelength is, I can get it from a displacement distance graph when the x-axis is the distance. Okay, it's the shortest distance between two successive crests or trough. Okay, or in layman terms, it just simply means it is the distance of one wave. Okay, and then again, the SI units is in meters, but sometimes it depends on the axis. It can be in cm, it can be in kilometers, etc. Okay, so you can take a look at this diagram. Okay, I have 3 waves. I start from the crest, so crest to crest, 1 wave, 2 waves, 3 waves. I have 3 waves over here, and these 3 waves are produced in 1 second. So my frequency is number of waves in 1 second. My frequency is 3 hertz, and then my period will be 1 over f, so it's 1 over 3 seconds. Okay, and then my wavelength is the length of one wave is actually 0.5 meters. Okay, then next, okay, I'm also going to introduce to you that there is another formula, okay, called the wave speed, okay, which is represented by V. Okay, so V can be obtained from displacement distance as well as displacement time graph. So wave speed is the distance traveled by the wave per unit time. So the wave will travel or move away from the source of disturbance. And how fast it moves, okay, is called the speed of the wave. Okay, so again, SI unit will be meters per second, but depending. So if you find the wavelength in terms of cm, the time in terms of seconds, it can be in cm per second. If you find the wavelength in terms of meter and then the time in terms of hours, it can be meters per hours. Okay, so the speed can be in different units, but SI units obviously is meters per second. So there is 2 formulas for wave speed. You can use V equals to lambda over T. Okay, that is the length of one wave over the time for one wave. Okay, it simply means distance over time. Or it can be the distance traveled by the wave over the entire time it takes for the wave to move from one area to another area. Okay, so total distance over total time, or the length of one wave, or the distance traveled by one wave over the time taken for one wave, lambda over T, or I can simply use V equals to F lambda. Okay, why is it F lambda? Because 1 over T is F. So I just sub in, becomes F lambda. Okay, V equals to F lambda is the more commonly used formula. Okay, rather than distance over time or lambda over T. But it depends on what question gives you. Okay, so let's take a look at an example. So I have over here a displacement distance graph. Okay, that means I just take a photo is at one instant, one particular timing. Okay, because this one is distance, so it's at one particular timing. Okay, I take a short snapshot of the wave. Okay, so these are many different particles all at that instant, at that one timing. Okay, from here I can get the amplitude. Okay, and the wavelength, the length of one wave, because it's the distance graph. Okay, so amplitude will be the maximum displacement. So amplitude will be over here, maximum displacement. From the rest position. Okay, I can be the height of a crest or the depth of a trough. Okay, so it will be 2 and 2 over here. Take note that amplitude is a scalar. There is no negative, although the displacement, maximum displacement is -2. Displacement is a vector quantity, but amplitude is not vector quantity. Amplitude has no direction. So the amplitude is just the maximum distance from the rest position. Rest position is the x-axis. So it's 2, and then look at the unit cm. Okay, it's the same for both graphs. Okay, because both graphs represents the same wave. Okay, so the amplitude over here is also 2. Okay, so this is the amplitude. Okay, so the amplitude is 2 cm for both graphs. Okay, the y-axis is cm. Okay, wavelength is the length of one wave. So wavelength, I need to look at distance, the length. Okay, so wavelength, so if I were to start from the origin, so one wave will be from here, go up, and then we highlight for you, one wave will be we do it in green. So one wave will be here, go up, and then come down. Okay, so this will be one wave. Then I'm going to repeat myself again, go up and come down. So one wave is actually 4, and then look at the units on the axis is 4 cm. Okay, I couldn't get the wavelength over here because this is time. Okay, wavelength, length of one wave, 4 cm. Okay, then what about period? Okay, so amplitude, wavelength, and period can be found from the graph. Okay, can be found from the graph, everything in blue over here. So period is the time for one wave. Like the period is time. So like for example, one period is 20 minutes, so it's a time. So the time for one wave, so if I were to start, okay, from the crest, okay, is to the next crest lah. Okay, so crest to crest, go down, come up. Then I'm going to repeat myself again, go down, come up. So it's already labeled for you, it's 3, and then you look at the axis unit is seconds, so it's 3 seconds for the period. Okay, so both amplitude is the same, but on the displacement distance graph, I get wavelength. On the displacement time graph, I get period. Okay, so amplitude, wavelength, period, get from the graph. Then other information I cannot get from the graph, I need to use formulas. So frequency and speed is two things that I need to use formulas. So frequency is 1 over period. So I will have my period is 3 seconds, is 1 over 3. 0.333 hertz simply means that there is 0.333 oscillations every 1 second. Okay, then after that, I can find the speed of the wave as well. So V equals to F lambda. So my frequency is 0.333 times my wavelength lambda is 4 cm. So my units will be in cm per seconds. Okay, so that's my wave speed because my 4 is in cm, my wavelength, 1.33 cm per second. This is how I interpret, okay, graphical representation of waves. Next, okay, I have another example. Draw another wave that has twice the amplitude and half the frequency. So I couldn't determine frequency, okay, but I can find the period, okay, or you can go about thinking frequency. What is the definition of frequency? Is how many waves in 1 second. Okay, so I can assume that, okay, so over here you can see from this graph, I have 2 waves. One wave go up and then down, go back to the original position. This is one wave. Then I go repeat again, go up and go down, second wave. I have 2 waves. So if I have half the frequency, I have, instead of generating 2 waves, I have only 1 wave within that time. Okay, and I have twice the amplitude. Amplitude is the height. Okay, so what am I going to do is I need to be very accurate in my drawing. I will make markings. I will make markings at the equilibrium position, the rest position, and at the maximum displacement, the amplitude. So my rest position, okay, I will start. Okay, let me do. Okay, so I put my rest position. I'll start from the same point, but now my amplitude will go up. Okay, so instead of having one complete wave here, I am only going to have half a wave because I half the frequency. So instead of one wave every 1 second, I have half a wave in 1 second. So I assume that is 1 second. Okay, so half a wave. So I only go up, haven't come down. Okay, so I want to have twice the amplitude. So instead of one box, I need exactly in the middle, I need to be up 2 times, 2 boxes. Okay, so this is half a wave, you can see. So I'm now going to sketch. No, my sketch is not very nice. Is it? Okay, usually I'll make markings first. It helps me to later draw it easier. Okay, so this is one half a wave, and then I'm going to continue. Okay, so within this period is again one wave. It will be my second half of the wave. So I will end up here. Okay, and then now I'll go down, go up, and now I must go down. So my second part of the wave will be like this. Okay, so this will be what I will have, twice the amplitude and half the frequency. Okay, the number of waves generated every 1 second decreased by 2 times. So instead of having 2 waves, I only have 1 wave. So this will be my new wave. Okay. Okay, you may scan the following QR code to try to work on more examples of a longitudinal wave and a transverse wave. So a summary, transverse wave are waves where the direction of vibration is perpendicular to the direction of the wave travel. So the particles move up and down, perpendicular wave travel, if the wave travel is moving to the right or to the left. Okay, transverse wave, there's many types, light wave, water wave, rope waves. Okay, longitudinal wave in your syllabus only sound wave and sometimes slinky coil or earthquake. Okay, longitudinal wave is one that the direction of vibration of the particles is parallel to the direction of the wave travel. Okay, and then we know that we can represent our wave in terms of a displacement distance graph. Okay, that means I take note of all the particles at one timing, one instant, and I will get the wavelength because it's a distance graph. I get the length of one wavelength. Then I can also represent it in a displacement time graph. So displacement time graph is the time changes, but I only look at one particle. So one particle, how is that one particle moving over a period of time? Okay, so it gives you about the time for one wave. So that is the period. And from the period, I can calculate the frequency based on frequency equals 1 over t or t equals to 1 over f. Okay, so I can get the frequency of the wave. And from both graphs, okay, I get the wavelength, I get the period, I get the frequency. I can calculate my speed of the wave, which is v equals to lambda over t or v equals to f lambda. Okay, okay, I will stop here for this third part before I move on into the fourth part.